My name is Kevin Lin, and this is my lab report for Introduction to Physics 1, Physics 2211, and this is my first lab involving constant velocity motion in one dimension. So the main question for this lab is how involves Newton's second law in real life, and how does it compare to our experiment as in a vacuum. So first we'll begin by discussing Newton's first law, which states that an object remains in motion if it is motion, and an object at rest remains at rest unless the external net force is applied. So this model involves constant velocity, which infers that there is no acceleration or net force. And some of the equations that we were interested in is listed on the slide. So I will first begin by elaborating on the steps of the lab, starting from analysis of the observed motion, and then constructing the model of the predicted motion glow strip, and then comparing and discussing the two models as well as their significance. For this lab specifically, I will be using a trig wall where the cause a flat surface in a straight line. I will then arbitrarily set the center of the mass at the center of the ball, and then take the diameter of the ball as 0.0381 meters. This will allow us to set the scale for tracker. A more in-depth overview of the lab experiment will now be provided to answer our main question. We will now analyze the ball's motion with tracker. So here in this We will now analyze the ball's motion with tracker. So here in this slide, we will only select the frames that crop out the initial and final frames where the ball is speeding after a push and then later slowing down due to friction. We will only be interested in the x-axis since we are observing motion in one dimension, specifically in the positive x direction. In our predicted model, the mass should be irrelevant because it is a constant velocity, meaning that there is no net force, which is adjusted for in the while loop based on Newton's second law in the positive x direction. So in the group fit model, we see the origin representing the initial position as well as the initial velocity, which is found by taking the average velocity between the first two position points. The intervals on the model are also set to begin at 0 with time for intervals of 0.042 based on what tracker has provided. Visualizing the code, we can now see the plotted position versus time and the velocity versus time graphs. The attached code segment of GlowScript shown on the slide will be attached in the YouTube description. Now that we have both the observed and predicted model, we can see that both the position versus time graphs are sloping upwards in a positive x direction. Similarly, the velocity versus time graphs are flat, which we can see after taking the slope or finding a derivative. This means that there is constant velocity and thus no net force or acceleration. So the slight differences between the two lines in the graph could be due to the precision of the tracker, the fact that the observed model in the real world, and thus the fact that observed models in the real world and thus friction exists as well as air resistance, and then there are other factors to consider. So in conclusion, I would say Newton's second law is an effective method to predict motion. However, there are several points to consider. An experiment in a vacuum such as the one modeled by GlowScript does not account for factors that are experienced in observed models such as friction, air resistance, and other extraneous causes such as the texture of the surface, some incline, and so on.